So we are going to look at a couple of examples where we're going to use the first derivative test to find relative extrema, as well as the intervals of increasing and decreasing. And we kind of laid those steps out last time. So take a kind of look at those up above as we walk through our first example. Now, the first thing I think is always useful in any of these functions that we're going to be working with is to first think about what their domain is. And in this case, if you think about the 2/3 as like a cube root, a cube root has a domain that is all real numbers. So just kind of worth mentioning here, there's not a restricted domain in this case. So even index radicals, yes. Denominators, yes, we need to look at. And so some of those things will be important as we go along. In this case, just kind of worth the mention, no restricted domain here. All right, so let's go ahead and jump in and let's take our derivative here. So our derivative is going to be our product rule. So as we are setting up our outermost structure here, we're talking product rule. So first one left alone, x times derivative of the second factor would be our 2/3, x minus 10 to the 2/3 minus 1, so our negative 1/3, times derivative of the inside, but that's just 1, plus changing that order, the second function left alone, and then times the derivative of x, which of course is just 1. All right, so we definitely need to simplify this because we have to work with it, right? We have to look for where the critical points are. We have to set it equal to 0, look for where it doesn't exist, and so on. So the first thing I would always tell you to do is it's hard to make sense of negative exponents until we rewrite them in a way where they're a positive exponent. That's often a good starting point. So let's take a look at this whole first term here. And so when you think of this x minus 10 to the negative 1/3, it can move into the denominator where it's x minus 10 to the positive 1/3. Now, also notice here, this is all multiplication of factors. The x times the 2/3 times that binomial. So we can really write this all as one term. So all we have in our numerator now is the 2 and the x factors, and then also that 3 is in the denominator. Now, the second term, and notice just by doing that, this is already looking better. So the second term was already to a positive exponent, so I would probably just leave that like it is. And then what I would probably do is think about multiplying in order to get a common denominator. So I would think about multiplying this second term by the denominator of the first term, of course, as a version of 1. So, the 3 quantity x minus 10 to the 1/3. So getting this simplified as one term is typically how I like to go, although it's not a requirement. You could have stopped at that point and just set it equal to 0 and maybe moved one term to the other side and cleared the denominators. That would have been just fine as well. All right, now try to do some problems in different ways like that as we kind of go through these next couple of sections here. So let's continue though as we're adding to get our common denominator. We already have it. So from the first numerator, we just have our 2x. From the second numerator, we have x minus 10 to the 2/3 times x minus 10 to the 1/3. Multiplying with the same base, you'd add your exponents, and that would be to the 3/3 or to the first. And then we still have the 3, of course. So that second numerator just became 3 quantity x minus 10, and that really looks a whole lot better. And then, of course, this is all over our common denominator. And so just kind of finishing out this simplification process, I would simplify my numerator, so we can certainly distribute through that 3, and then that'll put us in a position where we can just combine our x terms in that numerator. So it looks like we're going to have a 5x minus 30 all over our 3 times the x minus 10 to the 1/3, or if you prefer, a cube root. Okay, so this is a pretty good looking form here for our f prime. So we have found and now simplified our f prime. So remember, our first step is to find the critical points, looking for where f prime is equal to 0 or does not exist. Okay, so that's what we're doing here. So we are going to look for where our f prime is equal to 0 or where our f prime does not exist. So this is really all within that first step of identifying our critical points. All right, so now the benefit of having done kind of the upfront work there, we have a simplified fraction for our f prime. So a fraction goes to 0 if it's simplified to one fraction where its numerator goes to 0. So 5x minus 30 equal to 0. And you could either think about factoring out the 5 and then you'd have times the quantity of x minus 6, or if you prefer, you could just add the 30 and divide by 5, and then we get x equals 6. So there is the first critical point, x equals 6. Now, where f prime does not exist, that's going to be wherever a denominator could go to 0. And so we have 3 times the quantity of x minus 10 to the 1/3 equal to 0. However you want to think about that, divide by 3, cube both sides, but basically this is only going to go to 0 when that binomial x minus 10 goes to 0. And of course that is going to be at x equals 10. So here's our other critical point. So notice in this case these are both, by definition, critical points. These are both locations where they are points on the original function, meaning both the 6 and the 10, if you plug into the original function, they are points on the function. And of course, they're where f prime equals 0 or does not exist, so these are our critical points. So this was our first step, was to find our critical points. Now, second step is the sign analysis. So let's go ahead and do our sign analysis. So I think I'll put my sign analysis right over here. All right. So we put these numbers in order on our number line, these critical numbers. So we have 6 and 10. And remember, you are subbing into f prime. And the idea is using those conclusions, or those signs, to make conclusions, rather, about f. So we have to pick some number in these appropriate intervals here. So we want to pick something less than 6. So whenever possible, I like to pick 0. 0 is nice to work with. And we're subbing it into f prime, which happens to be kind of right up above us here in this boxed answer. So sub 0 into the numerator, 0 minus 30 is going to be a negative, divided by negative 10. Cube root of a negative is negative. So a negative divided by a negative is going to be positive. And so remember what we talked about last time, where a function's derivative is positive, that means the actual function, the original function, is going to be increasing. All right, let's sub in something in between 6 and 10. So, I don't know, maybe just 7. And so in the numerator, 35 minus 30 would be positive, divided by, in the denominator, it's still going to be a cube root of a negative, which would be negative. Positive divided by negative is negative. And remember, where a derivative is negative, that means the original function is decreasing. And one more time, a value bigger than 10, so something like 11. So 55 minus 30, definitely positive in the numerator, and this time also a positive in the denominator. Cube root of a positive is positive. And so we are back to our original function being increasing. And so now we also know that at x equals 6, this, if I have changed from increasing to decreasing, this is going to be the location of a local max. X equals 10, if I'm changing from decreasing to increasing, this is going to be the location of a local min. So let's just write out all of our final conclusions here. So we just said that we have a local minimum at 10, and then it's always subbing back into the original function. So if you were to sub in f of 10, you would have the binomial goes to 0, and then that's going to make the whole thing 0. And then we have a local max at 6. And then subbing that back into the original function, that one doesn't come out quite as nice. We could go to our calculator, but we're going to have 6 and then times 6 minus 10 would be -4. So it's going to be this -4 to the 2/3 power. Doesn't come out super nice. Let me just go to my calculator here. Okay, it looks like it comes out to be approximately 15 point. So if you wanted, or if you were prompted to go to a decimal, 15.12 approximately. But that's our local max. And then we have some intervals here of increasing and decreasing to identify. So let's go ahead and write those out. So we are increasing on the interval from -infinity to 6, and then union 10 to infinity. And then we were decreasing, and you can either use the union or the comma. Some books use a union, some books use a comma. And then lastly, we were decreasing in the interval from 6 to 10. And so not every problem will ask for all of these pieces, but you get them all kind of for free once you're doing your sign analysis. You can find the extrema as well as your intervals of increasing and decreasing. All right, let's look at one more. So I was mentioning in number 1 that I think it's a good idea that when you first look at a function to identify, get into a habit of looking for restricted domains. So let's take a look at this one, the natural log of 25 minus x squared. So one of the first things that I would encourage you to think about here would be its domain. So domains of log functions, logs have to be positive. So what's inside the log function needs to be greater than 0. Now, if you think about solving this, maybe you think about factoring it, and you have two kind of solutions to where it's equal 0 at both plus and minus 5. But when you're solving polynomial inequalities, you actually have to do this kind of the same thing we're doing here. It's a sign analysis of sorts. So you can't just like set them each greater than 0 or something like that. So what we want to think about is putting these on our number line here and then just subbing some numbers in. Like if I sub in -6, I would have 25 minus 36, and that's going to be negative. If I sub in 0, 25 minus 0 would be positive. If I sub in 6, again, 25 minus 36 is going to be negative. And what do we need? We need where it is strictly greater than 0. So we need where it is positive. You could also look at your graphing calculator if you wanted to kind of see, but just sort of recognizing that your domain on this function is restricted. So this function has a domain from -5 to 5. So I just think that's often a useful thing to get into the habit of as we first get started here. All right, so let's take a look at our first derivative. And so we're going to look for all those good critical points. So f prime, derivative of natural log of a function, is 1 over that function, and then by chain rule times the derivative of the inside, so times a -2x. So we're pretty much in a simplified form right away on this one. So that's kind of nice. We just have -2x over 25 minus x squared. So this one's actually much easier in terms of at least the algebra on the derivative. All right, so critical points. We're looking for where our derivative is equal to 0 or where the derivative does not exist. And so it's a simplified fraction, so the derivative goes to 0 when its numerator goes to 0. So -2x equals 0, divide by -2, and you would have x equals 0. That is in the domain, obviously there, from -5 to 5. So there's my first critical point. Now, if I think about where the denominator goes to 0, this, of course, is where g prime does not exist. 25 minus x squared equals 0. again, either think about factoring it like we did up above, or the other way to go on that would be to add the x squared to the other side. And then when you take the square root, you have to remember to introduce the plus or minus square roots. So you get plus or minus root 5. These are technically not critical points, and let's observe why. These are actually not in the domain of G. So by definition, not a critical point. But kind of just useful to remind ourselves that those are sort of like the endpoints, let's say, of the domain of G. So as we do our sign analysis here, once again, we're doing sign analysis on G prime, so we can make conclusions about G. And so we really want to be mindful as we're subbing in here of our restricted domain. So we're only subbing in values in between -5 and 5. So the function simply does not exist outside of these intervals. And so our only critical point here is at x equals 0. So that is the only critical point that's actually going on my sign analysis. All right, subbing in something between -5 and 0 would be, subbing in something like -1. And so we're subbing that into our G prime rather. So -2 times -1 is going to be positive in the numerator, divided by 25 minus 1. -1 squared would be 1, would be positive. Positive over positive is positive. And so if I am positive in the derivative, that meant the original function was increasing. And subbing in something between 0 and 5. So subbing in 1. -2 times 1 is a negative. Divided by 25 minus 1 is positive. Negative divided by positive is negative. So the original function is decreasing. And again, if I have changed from increasing to decreasing, this means we are going to have a local max at x equals 0. Now, just as an FYI, if, let's say you hadn't identified the domain and you made an attempt to sub in something like, let's say, over here, you hadn't yet noticed that issue and you were just plugging away and you're like, okay, I'm going to plug in something like 6. What would happen is you would, by the time you would, sub this back in, if you were to try to sub, let's say, 5, then let's say that this came out to be, what happens if I sub in 6 here? I would have a negative over a negative, so ultimately I'd have positive, and I would say, oh, that's increasing. If I then thought that I have changed from decreasing to increasing, and I was tempted to maybe think that 5 was a min, you might be alerted to that issue if you were to actually then attempt to sub 5 back into the original function, and you would actually get that it wouldn't exist because you'd have natural log of 0. But in any case, here's what we find out, and so let's just go ahead and write out our conclusions here. So we have our local max. So I have a local or relative max at 0. And if I sub that back into the original function, natural log of 25. And then I am increasing on the interval from -5 to 0. And lastly, we are decreasing on the interval from 0 to 5. So there's all the information that we get from our sign analysis there. All right, so next time when we come back, we're going to take a look at another feature on graphs, really important, called concavity and inflection points. So that's what we'll take a look at next time.